And coming into the classification, so we saw the ingredient part. So this sealant is converted in two different classified products. So one is called as one part and other is called as two part. So the one part is a ready mix. You might have seen in the market a 300 ml cartridge or a 600 ml sausage pouch. So that is a ready mix material. So if you see a carpenter or a window sealer coming to our house, or somebody sealing your kitchen, or somebody coming to your bathroom and doing some joint applications with sealant, you would have seen them coming up with a small plastic cartridge and a dispensing equipment. So it's like a small dispenser. So this is called as an one part. The formulation, the ingredients, what we saw before, everything is being bundled and put inside the cartridge. So while packing, it is being packed in certain atmosphere and where it does not trigger any reaction to happen within that particular tube. So once you open, cut it and then apply, this reacts with the moisture in the air and starts to cure. So this way the product starts curing by reacting with the moisture in the air. So when the moisture enters through the sealant after application, then there is an initial cure which happens on the area which is in contact with the air. And you can see the paste form of the silicone is getting converted into a rubber form. Okay, so then the moisture penetrates slightly through, then you can see that the rubber component becomes more and more deeper. So, but with a single component, the constraint is if you have only an one side exposed cure to the air where the moisture can penetrate, the maximum depth what you can do with single part is 15 millimeters. So beyond 15 millimeters, the reaction will be very, very slow. So you won't get a fully cured sealant to give you the desired mechanical or the physical properties. So this can be changed by having a dual airflow systems by using an open cell spacer or an open cell baker rod. So where then the air can be allowed to pass through from both the ends and then the depth can be increased. But essentially for a single seal with a one-sided open-ended applications like what we do in the weather seals, the maximum depth what is can be cured is only 15 millimeters. So, and this cure rate takes time. So the time it takes to cure 15 millimeter is general thumb rule is 2 weeks time. So a 1 millimeter per day is the general thumb rule for joints which are done beyond 10 millimeters. But if you really look at the applications, we don't do except on some of the structural joint applications 15 millimeter. So what is important to understand is by filling more and more sealant into a joint for a wider depth using a single part, we are essentially not achieving anything beyond 15 millimeters. Okay, whereas this particular limitation, or what we call it as the constraint, is completely not there for the two part. The two part, it does not require the moisture to react and cure. This automatically, when the two components of the sealant like part A and part B, they are mixed together. So there is a catalytic reaction which happens, and then the sealant cures, only the byproducts get released. Even on a single exposed joint applications, you can go to a depth of 30 or 40 millimeters, and essentially that cures in say 24 to 48 hours time. So the rate of cure for the two part is much faster than the one part. So that is the only difference between these two. So for a project which are of large scale and where you don't have a space to keep the panels for cure and you want to move them out faster in a day or two, then two part is one of the preferred product used by most of the high-end and fabricators or the facade manufacturers, because they want the panels which are done today to be dispatched or ready for inspection tomorrow. So this can be easily achieved by using two part. Other than essentially between one part and two part, there is no change in terms of design. So it can also happen that the broken glasses in a unitized system on a facade needs to be fixed using one part, because sometimes two part is not possible to be applied or done, though there are some new products which have been introduced by some of the manufacturers have come in to do that. But essentially, if you look at most of the times, the one part is always used for those applications where you cannot move the pump to the site or do some applications with two part. So the design in terms of the load or the capability for both is different, only the cure rates are different. Okay. So now we are going to essentially look at one of the application called structural glazing. So what is structural glazing? It is the method of retaining glass to the frame using silicone on all four sides. Okay, so any load coming onto the glass is transferred to the frame through the silicone. So we are going to talk about this in detail, and essentially if you look at a picture like this, like a building, wherein the areas where you can clearly see, this is the area where we are going to talk about the facades, is the structural glazing part. So this is a curtain wall. So in India, probably still, when I say curtain wall, most of the people might think that this is a mechanically fixed system. So what is interesting to understand is the glass can be fixed to the building in different ways. The way we are talking about here is using a silicone sealant to bond the glass to the frame. So this is one of the very proven technology, very energy efficient method, and it has to go through a series of quality check for doing this application. So which we will which I will take you through. So other than that, silicone can be used for various other applications. It can be used for fixing solid materials like a composite panel or high pressure laminate or thin stones. It can be also used for elastomeric coatings can be given on the rear facades where you want a good excellent waterproofing to be part of the facade. So it was also, we have got insulation blankets, which are very thin amount of insulation blanket, we can achieve very high insulation. And also what is also essential to understand is there are some new technologies coming up which can give you a crystal clear method of bonding a glass to the frame, or in a fin, or could be in weather seal, or on the point fixing, where there are essentially a clear technologies which are coming into picture, where you can avoid drilling a hole in the glass in the sometimes in the facade. So on the essentially coming back to the structural glazing part, the way the silicone is applied on a facade today is characterized into classified into two types. One is called fully unitized system and semi-unitized system. So the fully unitized system is normally these frames are floor to floor in height, or could be different dimensions where multiple panels can be put in one frame. So they take the frame in the horizontal direction, put the glass in a double-sided tape to hold it in place and apply silicone around the perimeter, and then allow that to cure, and after it is cured, this frame is moved to the side and fixed. So this is called as fully unitized system, and essentially these are done in a factory atmosphere where there is a clean and dust-free room is maintained with temperature control. The advantage is you don't see any grid work done on the building except the fasteners part, and this gets clamped onto the fasteners, and then there's a male-female joint which are again fixed onto the building, and you can do the completion very fast. So you need a capability to do a fully unitized system at factory, and you also need a good capability to handle these large units which are much heavier to the site and fix them. So, but this is essentially available in India. There are many top class facade manufacturers today who are successfully doing many projects using fully unitized system. The second system, which is also predominantly common and used in India, is semi-unitized system. Not only in India, these are the two systems which are being used worldwide, is so fully unitized and semi-unitized system. The semi-unitized system, you will find a grid work in the building, so which is we already put on the building, and essentially there will be a subframe in the factory, and individual glasses will be bonded to each and every subframe. This subframe will be then fixed to the main frame. So again, it is not only glass, you can use different materials to bond silicone to the frame, and this subframe can be then moved to the side and fixed to the main frame, and you get a externally what you see is a clean, good facade. And also there is one more system which has been also used for some of the applications, essentially on a fin total vision system, or a fin system, or a two-sided captive system is a stick. So again, the glass will be mechanically held by other systems, and the silicone will be used to bond either two sides. And this is again a lot of quality control needs to be done, because when we are going to apply silicone at site, the site conditions. The site conditions are not always dust free or not clean, or it is not essentially maintained with the temperature, so it's hot, humid, dust. So we need to ensure that the proper cleaning is done before the sealant is applied, and the sealant is applied properly with the right temperatures, and also the quality checks of this needs to be done. So this needs a lot of quality control. So essentially somebody is doing a four-sided fixing for a broken glass. Again, it requires a vigilant mechanism to monitor. So it is not generally advisable to do this as a system for a whole project. If you have broken glasses here and there where we can exercise the quality control, then this is one of the methods which has been followed today for bonding the glass, but not for the complete project. Okay. So this is showing you the picture on the fully unitized system. You can see there is a large frame with multiple panels in one frame. Okay. This is fully unitized, and this is semi-unitized, wherein there is a single subframe where the glass is bonded, and this is then fixed to the main frame using mechanical cleats, where the glass is bonded to the subframe using silicone sealants. So the case history is what it has been shown here, or all the projects which are done with a fully unitized system, and you can also still see some of the systems have a two-sided mechanical capping because of the requirement and an architectural feature, or sometimes they are also designed to take the loads. So what is essentially critical to understand here is you can also see these are the projects which are like the world's tallest tower standing today, which is the finished structure Burj Khalifa, has been done with such a system. And also the type A 101, which has got a lot of earthquakes and typhoons. So, and also you can see the climate like Malaysia, which is similar to what we have in Indian coastal climates, again the Burj Al Arab. So these are all the cases which have been standing tall for 10, 20, 15 years, and then these have proven that the technology what is being used for the product is really working. So what is the difference you saw from the previous picture to this picture is here you don't see any mechanical fixing or an aluminum which is holding the capping, which is holding the glass from outside. So what does it essentially mean is all four sides of the glass is bonded using silicone sealant. Okay, you can get a completely clean facade by using this technology, so you don't need to have an additional mechanical feature to hold them. So what you have to do is we need to design and then apply and then install. So what is possible is these are the new trends, and you can see in India many projects which have been done using this technology in last 15-20 years. So I want to quickly take you through one of the important slide on this particular application is the dissection of a structural joint. So this is the glass and this is aluminum. So the glass is bonded using silicone which is applied behind the glass. So this is called a structural silicone, and this is what we have been talking about so far. So any load coming onto this glass is transferred through this silicone to the frame. So the contact width between glass to the frame is called as the structural bite. So this needs to be calculated, and this is calculated based on a formula which is again designed on a rigid plate blending theory. So how you when you bend the rigid plate, so what is the trapezoidal distribution of stress coming out. So based on that, the formula has been developed for this technology, and this is proving out to be the successful formula for last 45 years. The thickness of this particular silicone is called as glue line. The function of the glue line is one, to gun the silicone into this joint, and second, when there is a thermal movement happening between the glass and aluminum, this glue line accommodates that thermal movement. Okay, so this takes the load and this takes the movement. And what is that you see here is also a spacer tape. So the function of the spacer tape is to provide the gap and also to keep the glass in place till the sealant cures. You might have seen in many applications where there is a single glass being used and there is a double-sided tape is being applied. So essentially you can see that the adhesive would leave the glass in no time. Okay, so what is holding the glass permanently to the frame is silicone. So we need to understand this is the product which is going to be holding that for the long term. So this you may not see from outside, because nowadays people use performance glasses, people also use double glasses. So what we generally see from outside is the weather silicone. Again, there is a minimum joint design required for weather seal in terms of the width and depth, and this is what is really providing you against the watertight seal. Okay, so the essential components what you see here is glass, aluminum, whereas there are two types of silicone is being shown here. This is called a split joint design, where the silicone is applied from inside. There is a spacer, and somebody also can use a baker rod here, and this is the weather silicone. So this is the formula I was talking to you about, how we have derived at the formula for determining the structural bite is by doing a stress distribution theory using the trapezoidal way. So here the maximum stress, you can see how it is happening around the 50% of the short side and somewhere here on the long sides. So the formula comes by multiplying the 0.5 into short side into wind load, which is in the kilopascal, divided by the sealant design load. In most of the cases, this the 0.5 and sealant design load is almost common. Depending upon the glass size and the wind load, you can essentially determine the structural bite. So the concept is same for a single and double glass. So in case of a double glass, this is a double glass which is made from the glass processor's factory, the structural silicone is applied behind the glass, okay, inboard glass. So this is a fixed unit where you can see the sizes of both inboard and outboard DGU is, glass is same. So in that case, you normally apply the silicone behind the inboard glass of the insulating glass unit. So this is a spacer tape. Again, it's a fully unitized system. You can see a male and a female joint, and also you can see the weather seal here, which is controlled by putting a baker rod here. So there are three types of sealants being shown in this picture. One is the structural sealant, second is the insulating glass, and the weather seal. Just to give you a idea, so there are three products and they have different application requirement. The structural silicone is used for holding the glass to the frame, and any load coming onto this unit glass is transferred through this to the frame. The insulating glass sealant is designed to keep these two units together. Weather seal is acting as a seal not to allow the water to come in and take the movements. So any of one of this fail, if a weather seal fails, water will come in. If the secondary seal of the DGU fails, you will have a fogging, and if this fails, you may have this glass coming down. So they are very critical. And also in terms of the quantity, if you look at normally a glass of 1.5 meter by 2 meter or a 2.5 meter with a wind load of 2 kPa, generally the silicone required to support it against wind load is hardly 12 millimeters. Such a huge glass, a 3 square meter glass, what you need is essentially 12 millimeters of silicone. But the criticality wise, what is important is designing the product, applying it, and then selecting them is very, very, very important for this to perform. And it is like any other thing. It is not that you need to do extra care for silicone. It is essentially important for any manufacturing process that you need to have a proper design, proper product, and proper application. So just to sum up, what we have seen here is the silicone is taking loads. So what are the loads it takes up? There are large area load which comes onto the building, which is called as the wind load. This is a full area load. So the wind will be hitting the building either through the positive or the negative. So the positive is a compression, and the negative is the suction. So when the glass is pulled out, what is holding the glass to the frame is essentially the silicone sealant here. Okay. So this is the sealant which is essentially holding it. So this has to be designed to take against the wind loads. So which can be designed. We have seen the formula. The second thing what we need to understand is sometimes in the facade, we may have provisions not to have the, we may not be able to support the weight of the glass. So which is not a good practice. Essentially, we need to support the weight of the glass as part of the section under setting blocks, using setting blocks. So if not, what happens is this silicone is also have to be designed to take the weight of the glass, which is a shear. So there is a different formula which has to be followed to take the weight of the glass. So which will depend upon the weight and the perimeter of the sealant length, and also the sealant design factor for the dead load. Okay. So it could be possible that in some of the facades, you may not have just a straight facade, you may have an inclined facade. So you have a dead load support, but still there is some angle of inclination because of which there is a load acting on the sealant. So we may have to determine both wind load and dead load, see which is more. And we need to see the combined stress and recommend the bite according to the stress which is acting on the sealant. So we saw wind load, we saw dead load, and also there is a differential thermal movement. There are climates which are like you go to Hyderabad, Delhi, Bangalore, Pune, you may have a minimum and maximum which is quite high. Essentially, you may have a minimum of say 15, if you go to Delhi, it is minimum of say 5-6 degrees, maximum of 45 degrees. This is an air temperature. When you talk about the air temperature, the substrate temperatures are much, much higher. So there is a temperature gradient of close to 70 degrees we are talking about. So there is going to be a thermal expansion and contraction which is going to happen between glass and aluminum. So essentially when there is a thermal expansion and contraction happening, the silicon, which is a tough rubber, but it is also flexible. So it has to allow certain amount of movement to happen. It's not like a chewing gum that you need to allow that to movement, otherwise nobody will go near the building. What we are talking about is the rubber, which is tough but flexible, but it accommodates the movement so that the glass moves, and then you accommodate the movement so that it does not lead into any failures. So the silicons do that, and there are the movement capability has been built in as part of the product characteristics, which is also considered while designing the product for this joint design. So I am quickly taking you through some of the way how do you calculate the byte. So if you take a glass size of 2000 by 1200 millimeters, and if you see how to calculate the wind load is, if there is a design wind load of 1.5 kPa, so you take 0.5 into the short side into the wind load in kPa divided by sealant design load, which is 140 kPa. You get 6.5, round it up to 7, and add a millimeter tolerance, and always maintain 8 millimeter, so that your glass is essentially designed to take care of the with the silicon to take care of the wind load. So when there is dead load support, the silicon will take the wind load, and here the setting blocks are taking the weight of the glass, which is again transferred to this dead load to the section. But in some cases this may not be done this way. So where the dead load is also taken by the sealant, again this is a formula where we need to use for calculating the dead load structural byte, where the weight will act into play. So here the weight upon perimeter into this is the sealant design factor for the dead load. Okay. And an example to talk about is if you have a same glass size with a 6 millimeter thick where the weight is 36 kg, and if you apply the so you have a perimeter of 6.4 meters, and also you have a 36 kg, and when you do the calculations you are getting 8 millimeters through this. So we got 7 in the wind load and 8 in the dead load, so we have to use 8 millimeter for this particular glass to take the weight load. So whatever is higher we need to do that. So when there is a particular angle, then we need to actually take the angle of inclination and accordingly calculate the dead load stress for those buildings which are inclined. So this is essentially showing you how the movement happens with expansion and contraction because of the temperature change. You can see how silicon is moving. So essentially both the structural and the weather seal joints are tough, but they can move and take these movements. Just to recap on our first part, so the minimum structural byte has to be always determined by the wind load. Also the thickness has to be determined by doing the thermal dilatation calculations. If there is a dead load which is acting on the silicon, we need to determine the dead load as per the formula. A minimum 6 millimeter of byte has to be maintained in spite of calculations, and also a minimum thickness of 6 millimeter is to be maintained regardless of any calculations. So the byte should be always equal or greater than the glue line. So if you are doing an 8 millimeter glue line and your byte comes to 6 millimeter, then automatically to accommodate the equal, you need to make the byte also as 8 millimeters. So there is a ratio between the byte to the glue line, the width to the height. So 1:1 to 3:1 is the ratio. For a 6 millimeter thickness or the glue line, you can go up to an 18 millimeter structural byte. The important thing what is also essential to understand here is the structural joint should be easily able to fill into the joint. It should not be so complex. You can show in the drawing, but practically it may not be possible for you to apply. So such designs are not really a proper design for applying silicon. Okay, so one side should be always exposed to the air for the silicon to cure, which I explained in my initial slides. So these are all minimum guidelines. So you should always contact your manufacturer or the supplier's representative for any complications or design challenges. So essentially this is a technology which has been used for now 45 years, and it gives you an excellent benefit. You get a completely clean glass facade. There is a flexible anchor which is holding the glass to the frame. This takes wind loads. This can be designed to take hurricanes, typhoons. It's a flexible anchor. It can take seismic loads. It is UV resistance. It's a long-term weather resistance product. It's a flexible cushions. So it is one of the most reliable method which has been proven for more than 45 years. So it's a proven technology for us to really take that as a right method of doing the glass fixing today. Okay, so this is my first part, and I'm also going to take you through a small video in my now to show you on some of the essential things of how you really apply a silicone into a structural joint and what are the quality controls you need to follow while doing this joint application.